orbit. The orbit of Mercury's orbit. All right, so 1900s. Set the stage for us. What's going on early 1900s? What war? All right, World War One. What else? Yeah, 1900s. What's going on? The early 1900s. Like,
People are getting rights finally.
okay, so a little further in, interesting to see you define early 1900s as the Great Depressions, or no, we're not even in through that. Okay, pre-1950s. Gotcha. So older than your grandparents, I'm aiming. Just no. Okay. Just repeating what you said. Yeah. All right. So early 1900s, we've got the Industrial Revolution. We've got planes are just starting to exist. Okay, good. I'm glad somebody said Wright brothers. Let's see here. And World War One was put onto the table as well. Early 1900s, we also have an individual who, in his legendary patent office, is starting to write about gravity and light. Albert Einstein. All right, so Albert Einstein, I'm going to give a little bit of the history piece before I actually talk about what he published. I'm going to give the history piece before I give you what he published because it's very interesting that his information actually ever got anywhere. So Albert Einstein, everybody knows he's a patent clerk. Well, now you do, so everybody knows it. Ah. Right? Oh, so he's a patent clerk, and he's actively researching gravity and light. When I say researching, his favorite method of research is thought experiments. He'll do some reasoning through things, pose himself with a puzzle, and then logic through how that puzzle actually gets resolved. Basically. And in 1915, he publishes a paper on general relativity. Oh, yeah. That's the huge topic for today. But to understand a little bit more about why general relativity was so important, 1915. What's going on? World War One. Anybody know Einstein's nationality? German. So he's a German in World War One, and he's trying to publish information about how physics works. Who wants to hear what a German's got to say post World War One? Nobody. So one of the biggest issues that Einstein faced with trying to publish and get his information out, get his paper read by others, is the fact that nobody wants to read anything a German's publishing. They're currently to blame for a whole lot of death and not really being looked upon well. And if you want to make things even better for Einstein, what was Einstein's heritage? Jewish. So you're a German, no one outside of Germany wants to talk to you, and you're Jewish, so people inside of Germany are just starting to blame you for literally everything that's gone wrong. So eventually we'll get there. German and Jewish. So he faced all sorts of problems with trying to get his information read. Okay, so he does publish his paper, and actually, the fact that he was a patent clerk does work to his advantage because the patent office that he worked in had Swiss connections. And why is that important? Not Germany. Say again. Swiss cheese. Watches. Say again. Switzerland historically has a policy of maintaining neutrality whenever any kind of wars or that kind of thing erupt. So, because Switzerland is willing to talk to people from Germany, Einstein's able to get his information through Switzerland and then out to others. Which brings us to an individual by the name of Sir Stanley Arthur Eddington. I don't think so. All right. So Eddington was an astronomer royal for England. Uh, that is basically the term that they award the highest like ranking scientists in a field or that specific field. Astronomer, astronomer, yeah, yeah, basically. Um, And Eddington was able to take Einstein's publication on general relativity, and he is considered to be one of the few people who's ever truly understood all of the nuances of general relativity, other than probably Einstein himself and like Stephen Hawking. So the number of people who truly get all the implications as to how this stuff works, very, very few and far between. So no. Reads Einstein's work. Einstein's. The maybe we can give Neil deGrasse Tyson a little bit of benefit of the doubt here. I doubt he's anywhere near as good as Hawking was, but I mean, reads Einstein's work and makes predictions about a solar eclipse. Makes predictions about a solar eclipse. All right, so here's where we have to add in some of the information about general relativity and what exactly Einstein is saying. So, general relativity. Yep, I'll move it. So, in his first publication, Einstein tries to put to rest the debate about light. Um, Throughout the 1800s, one of the biggest debates in the scientific community was, is light a particle or is light a wave? And in special relativity, Einstein comes along and says it's both. Right? It seems like an easy conclusion to draw, but evidently we needed Einstein to come along to say it. And he goes further in explaining how the nature of light works in special relativity. But when he publishes his next thing, general relativity, he takes light's information, the stuff that he published in his first book, and uses it to explain gravity. So general relativity is the first theory that explains why gravity exists. First theory that explains why gravity exists. Okay? In that explanation, he goes on to say that any object that has mass warps the space around it. And so, as mass warps space, it causes effectively what he called a curvature of space, so that all space acts like an inclined plane or a sloped plane. And everything that's in that plane has to continue to follow Newton's laws, continue to try to travel in a straight line, but the line itself that it tries to travel on has become curved. So objects don't actually feel a force, according to Einstein. pick my sciences here. Objects don't actually feel a force according to Einstein, but they're traveling in a straight line, and the path they travel on is simply curved. So objects, I've got a demonstration or two here to go in a second. Right? I told you today was one of the top 4 for things that don't make sense. I know, but so far we've tried it and it works. Um, so objects do not pull on each other, but rather warp space around them.
I don't even want to write this down. I know.
So then the object traveling in a straight line now follows what would appear to be a curved path to an outside observer.
They're traveling on a straight line.
Yes. In a straight line, follow a curved path to the outside observer. So from your frame of reference, you travel in a straight line, or objects travel past you in a straight line instead. However, if you are then able to remove yourself from that perspective and recognize that you are only traveling in a straight line relative to the space around you, it is in fact the space itself that is curved. So if I were to say, let's do this way. We would all agree that this is a straight line, correct?
I
Okay?
mean, not really.
Give or take a little bit. Okay? And we can say an object is traveling on it, going in this direction. Okay? Object travels from point A to point B along a straight line. Everyone can agree that that is the shortest way to get from one point to another. However, Einstein's now saying, well, what if the paper is not flat? What if the paper contorts itself in some way?
Wait, so is this why airplanes follow like this path instead of?
Wait, no, it's not. Okay. So Einstein is saying that we don't live in a universe where space is a paper. We live in a universe where that paper
This
is
makes sense. I get
flipped
this.
around and twisted and bent based on the presence of a massive object. Oh,
I guess. Yeah.
the universe.
Stuff.
Yeah, all I can bend is a two-dimensional piece of paper. So, in terms of three-dimensional, it works better if you think about it as a density function. So, what I mean by that is that here I can curve the paper, right? But what it really would look like more if we were able to make this three-dimensional is if I were to take this paper and I were to make it more dense on this side and very lightly dense on this side, so that you'd have more collisions effectively through this side of the paper and fewer at this end, so that you have more warping on this side and less warping on this side. So we can look at it in terms of two-dimensional and just wrap around the paper. But if we want to actually represent it in terms of three dimensions, we have to be able to recognize that it works as a density function and it's just more condensed space in some locations and less condensed in others. When I like move this cabinet, density change flow. Yes, because the space itself that the object is taking up is warping in a different manner. Now, this has some interesting implications for gravity itself. Einstein has done away with this force and now saying that space itself is warped. One of the implications that this carries with it is that objects don't need to have mass to feel gravity. Objects that don't have mass could also feel gravity. So what is, yep. What can you come up with that does not have mass? All right. Electron does have mass. Chemistry teachers lie to you. It's about 1/1800th of the mass of a proton. It still exists. However, light does not have mass. Time also doesn't. All right. So, guys, I need your attention here. So this is one of the conclusions that Eddington actually reaches, is that if light doesn't have mass, which all indications at this point were that it doesn't and still doesn't, light feels gravity. No, sound is just a wave. It's particles. Because it doesn't need a medium. We'll get to that in a couple of units. Hey guys, I need the talking to stop. All right, so light follows curved space. And what this means is that Eddington predicts that if he can look at points of light that would travel by a large mass, the points of light should follow a different path than if the mass was not present. So if light passes by a large mass, it will follow a different path than if the mass was not present. So Eddington came up with an experiment to figure it out. And he looked at a set of stars in the sky where he knew 6 months ahead of time that there was going to be a solar eclipse. So what he did was he plotted the exact position of these stars, measured the distances between them, and then waited 6 months for the solar eclipse. And the solar eclipse was going to occur right in front of that patch of stars. So when the eclipse actually occurs, it becomes plenty dark out, and you can actually take pictures of the stars that would be appearing. It's a little tricky to do. Anybody get to see the solar eclipse that happened? Okay. So you get to see some stars, not many, but you do get the actual ability to see them. So when he went to measure the position of the stars, what do you think he saw? Clouds. He didn't get to see anything. It was cloudy the first time. So he actually had to run the second experiment. Yeah. He had to wait another like 3 years and travel to two different continents. So rather than getting his information right away like he was hoping, 6 months in advance, 6 months in the making, he had to wait another, I believe it was 3 years to get the funding and the locations. But this time he wasn't going to be foiled by clouds. And he sent one team to South Africa and one team to South America, both of which were on the path for the same solar eclipse. Both had the same set of information, and both were able to actually this time measure the location of the stars. And in fact, they did measure that the stars' locations had all moved towards the sun. So the sun being in front of these stars caused the path of light coming from these stars to bend towards them. What he effectively was observing, so if this is one of the stars, and this is Earth, normally the path of light would follow, would look like that. However, and let's put another star here for perspective. Normally it would be. However, when when we put the sun in the way, the path the light follows. Do I have another color? I need to get more colors.
Take your pick. I'm like 10.
I'm going to go with this one. All right. So the new path that the light followed looks more like this. If you look at the actual picture of this, it is a very small difference. Fractions are, let me get fractions. Well, probably about a couple arc minutes in actual. So Tycho could have measured it if he could actually see this, but it's pretty for most of us. Yeah. We'll get there. All right. So Eddington was actually able to provide concrete evidence for Einstein's general theory of relativity. Einstein's indicated objects don't need mass to feel gravity because masses simply warp the space around them. And Eddington has provided the evidence that Einstein's theory predicted. So he effectively is able to confirm for Einstein, yeah, hey, he's right. And not only is that important scientifically, but also politically, because now Einstein has some grounds from which he can actually start talking and pushing his information, and let's not be in Germany anymore. Habiba, then Caroline. I'm going to get there. Yep.
I googled it, and it's showing like apparent position and then actual position. So did the star just look further over than they knew it actually was?
That's what I'm saying, yes. No, the light coming gets moved. The star doesn't actually get moved. So where we look at it and where we see the star is in a different location, but obviously the star hasn't shifted.
But everything's moving. How do they know what did it?
And now it looks like that. It's exactly what we're saying. Yes. Okay. So, other things that we get from this. First of all, this presents the grounds and the first observation of what we call gravitational lensing. All right, gravitational lensing is a people's going to explode back there. Gravitational lensing is an effect that we observe where we can see magnification of objects that are far away due to a galaxy or stars that are between us and a faraway object.
What?
I've got pictures. Hang on.
Yeah, right.
That's what I said. Yes. The magnification of far away.
It's like
Gravity glasses. Yes. Because of the massive object. All right, so pictures, because we need pictures for this. Don't take advice from Trevor.
Out of sight, out of mind.
All right, so first picture that I've got for you. This is a picture of what we call the Hubble Deep Field. Every object you see there is not a star, it is a galaxy. Okay? And I want to pick out a handful of galaxies here. I want to pick out this one and this one, and if I remember correctly, this one. So first of all, you'll notice they're kind of making a circle around this group.
Because Doctor was pulling the light from behind,
Yeah, and not just slingshotting it towards us, But actually, the light from those three that I picked out, they're actually the same galaxy.
Because the light.
This light here, and this light here are actually three pictures of the same galaxy from different angles.
And it reflected?
They're being refracted. So the light's coming out, warping around. The light's coming out, warping around, and coming back. So we actually get light from the same location, billions of light years away, reaching us at the same location at two different angles.
That's actually beautiful.
Do you believe in aliens? Because like look at that and tell me you don't.
I definitely do.
Yeah.
But there's no possible way we're the only ones.
I can have that conversation when I'm not trying to teach a whole bunch of other things. So this is a cluster of galaxies that is warping this light. In this case, we can also see more defined versions here. So this is light from a distant galaxy. This would be the one in the center is the core of a galaxy. And this light is coming from 1, 2, 3, 4 different locations. Is actually one object that we would not be able to see. It should be hidden behind this front central object. This is what we call an Einstein cross. And it is simply 4 different reproductions of light coming towards us that have each warped around the central object.
How do you know it's fake? Like
How do I know it's not fake?
but how do you know how do people know that's not
Because they have the exact same light signatures. So when we look closely at each one of these, they all have the exact same patterns, the exact same makeup. Spectrometry. So we take a look at exactly what colors of light are coming from it, and then we pick out individual pieces. You know that thing you've done in chemistry? Yeah, it's that. We like that stuff. And then we do some of that involving where the colors should be and where we actually see them. And for a concept we call redshift. We'll get to that in a few chapters.
that would start
Say again? You don't need to. Effectively, yeah. Yeah. Yeah.
isn't it like a sundog?
Maybe I'm stupid, but like, why did we? Isn't light like?
It's simple.
Trevor, it's most complex
It actually
concept
is
so
so
much
much
entire history of man.
As long as you don't have
It's
math
simple.
anxiety, it's simple.
It's just
So I want to hear the rest of Habib's question. Yeah, it is. With a high enough mass in a small enough radius that the escape velocity from its orbit exceeds the speed of light. All right, so anatomy of a black hole. When we talk about a black hole, the picture that we see is just a black dot on a background of stars. The edge of the black dot is what we call the, oh man, the words are gone. I like that term, the event horizon. An event horizon is that edge of the black hole. I mean, in terms of that movie, it would fit about 2 classes. Because about an hour and a half in, it becomes everybody dies, and it's end of the movie. And I actually have shown that movie in class before. No, because black holes are billions of light years away.
Thank God.
No, not necessarily. Next up, next term here is the Schwarzschild radius. Because they think they're like really cool to talk about the destructive force. Schwarzschild radius. This would be the radius of the black hole from its center to the event horizon. I did. I think. Now you got me questioning it. Is there another CH in there? Yeah, that's it. SCH, Schwarzschild, yeah, radius is the radius of a black hole to its event horizon. And the last term that I want you to have here is the singularity, which is the center of a black hole where we believe all the mass is concentrated in an infinitesimally small space. Right? We already determined I don't do well on that.
How does it,
Wait. So our dark things.
And see you tomorrow.
I want to make